In July 2022, as the first deep-field images from the James Webb Space Telescope began to arrive, astronomers expected to see faint smudges, primitive galaxies just beginning to form. Instead, hidden within the data was something far more unsettling, a signal, sharp and luminous, emerging from a time when the universe itself was still in its infancy. This object would later be identified as MOM-Z14. At first glance, it appeared ordinary, another distant galaxy buried in the vastness of space. But as scientists analysed its light using Webb's near-infrared spectrograph, the numbers began to tell a different story. The galaxy's redshift was measured at 14.44, placing it just 280 million years after the Big Bang. To understand the significance, consider this. The universe is approximately 13.8 billion years old. MOM-Z14 formed when the cosmos was barely 2% of its current age. According to existing models, galaxies at this stage should be small, dim, and chemically simple. They should not yet have had the time to grow, evolve, or shine so brightly. But MOM-Z14 does. It is not faint. It is actively forming stars at an intense rate, producing a level of brightness that contradicts theoretical predictions. Even more surprising, its light carries the signatures of heavier elements, materials that can only be created inside stars and released after they die. This presents a fundamental problem. For such elements to exist, multiple generations of stars must have already formed and completed their life cycles. Yet the time available, just 280 million years, appears insufficient for this process to occur. The observation does not align with the expected timeline of cosmic evolution. The discovery, reported by international teams working with data from NASA, ESA, and the JWST Science Consortium, is not merely a new record. It is a challenge, a direct contradiction between observation and prediction. If MOM-Z14 exists as we see it, then the early universe was capable of building structure far more rapidly than current models suggest. And that raises a deeper question. What did the universe look like before this moment, before galaxies like this could even exist? To answer that, we must go back to a time before light itself could travel freely. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, detected a faint uniform signal across the sky. It was not interference. It was the afterglow of the Big Bang, the cosmic microwave background. This discovery confirmed that the early universe was once a dense, opaque state where light could not travel freely. But what followed was not illumination. Nearly 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Photons were finally released, and space became transparent. Yet instead of a universe filled with stars, there was nothing but darkness, no galaxies, no structure, only vast clouds of hydrogen gas drifting through an expanding void. This period is known as the Cosmic Dark Ages. According to cosmological models refined over decades, including simulations built on the Lambda CDM framework, gravity would begin a slow and gradual process. Tiny fluctuations in density would pull matter together, forming the first gravitational seeds. Over time, these seeds would collapse, ignite, and give birth to the first stars. But this process was not expected to be fast. Scientific predictions placed the emergence of the first galaxies at around 400 to 500 million years after the Big Bang. These early systems were expected to be faint and chemically simple, composed almost entirely of hydrogen and helium. Heavier elements would require generations of stars to form and die, a process that demands time. This timeline was supported by simulations, observational constraints, and decades of theoretical work from institutions including NASA, ESA, and leading cosmology groups worldwide. And yet, the discovery of MOM-Z14 directly challenges this sequence. Detected by the James Webb Space Telescope and confirmed through spectroscopic analysis, this galaxy exists at just 280 million years after the Big Bang. It is not faint, it is not primitive, it is already active, already luminous, and already evolving. In simple terms, something formed too quickly. If MOM-Z14 is real, and the data confirms it with high confidence, then the cosmic dark ages may not have been as slow or as empty as we believed. Structure may have emerged earlier, stars may have formed faster, the universe may have accelerated its own evolution. The stakes are no longer theoretical. Either our models are missing a critical piece of physics, or the early universe behaved in ways we do not yet understand. To uncover the answer, we must now examine the foundations of these models themselves and the assumptions that shaped our expectations. In 2010, long before the James Webb Space Telescope ever launched, cosmologists were already simulating the birth of the universe inside supercomputers. Projects led by institutions such as NASA, ESA, and major research universities attempted to recreate cosmic history using the Lambda CDM model, the standard framework describing dark matter, dark energy, and structure formation. These simulations were not guesses. They were precise, data-driven reconstructions built from decades of observation, including the cosmic microwave background and large-scale galaxy surveys. And they all told the same story. In the early universe, matter was nearly uniform, with only tiny fluctuations in density. Over time, gravity would amplify these fluctuations, pulling matter into halos dominated by dark matter. Inside these halos, gas would cool, collapse, and eventually ignite the first stars. But this process was slow. The first galaxies, according to these models, would be small, faint, and chemically primitive. They would take hundreds of millions of years to grow. Bright, massive, chemically enriched systems required multiple generations of stars, each generation forming, burning, and exploding before enriching the next. This created a clear expectation. Before 400 million years after the Big Bang, the universe should contain only simple structures. Nothing bright, nothing evolved, nothing like Momza 14. Yet, when the James Webb Space Telescope began returning real data in 2022, this expectation began to fracture. Momza 14, observed at just 280 million years after the Big Bang, does not align with these simulations. Its brightness suggests intense star formation. Its chemical signature implies prior stellar generations. Its existence compresses processes that were believed to take far longer. In simple terms, the models predict a slow build-up. The universe delivered something fast. This is not a minor discrepancy. Simulations are calibrated against observable reality. When observation contradicts simulation, it signals either missing physics or incomplete assumptions. The stakes extend beyond a single galaxy. If the foundations of these models are incomplete, then our understanding of how the first structures formed, how matter organized itself into stars and galaxies, may need to be revised. And to understand where the models may be failing, we must now turn to the instrument that revealed this contradiction, and how it measures the universe itself. On December 25, 2021, a rocket lifted a machine into space that would change how we see the universe. Built through a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, the James Webb Space Telescope was designed with a single objective: to observe the first light in cosmic history. Unlike previous telescopes, Webb does not look in visible light. It observes the universe in infrared, allowing it to detect radiation stretched over billions of years. Light emitted from the earliest galaxies arrives at Earth no longer visible, but transformed, shifted into longer wavelengths by the expansion of space itself. This shift is known as redshift. The higher the redshift, the further back in time we are looking. To measure this precisely, Webb uses its near-infrared spectrograph, or NIR spec. This instrument does not simply capture images, it breaks incoming light into its component wavelengths, revealing distinct spectral lines, patterns that act as cosmic fingerprints. In early 2022, during one of Webb's deep field surveys, astronomers targeted a small, seemingly unremarkable patch of sky. The goal was simple: search for the faintest and earliest galaxies ever observed. But the data returned something unexpected. Among the distant signals was a source that appeared brighter than anticipated. Initial imaging suggested an extreme distance, but imaging alone is not enough. Confirmation required spectroscopy. When NIR spec analyzed the object's light, the The result was definitive, a redshift of 14.44. This measurement placed the object, now identified as MOM-Z14, at approximately 280 million years after the Big Bang. The signal was not ambiguous. It was spectroscopically confirmed, reaching a level of confidence consistent with the highest standards in observational astronomy. In simple terms, this was not a candidate. It was real. The implications were immediate. A galaxy this distant should barely exist. It should be faint, barely detectable. Yet MOM-Z14 was clearly visible, emitting enough light to be studied in detail. The instrument had done its job with precision, but what it revealed did not fit expectation, because measuring distance is only the beginning. The true challenge lies in understanding what that light is telling us about the object itself, and as scientists began to analyze its brightness and internal activity, a deeper contradiction began to emerge. In 2023, as detailed analyses of JWST data continued across international research teams, a new problem began to emerge. It was not about distance. That had already been confirmed. It was about brightness. MOM-Z14 was not behaving like an early galaxy. At a time when the universe was only 280 million years old, galaxies were expected to be faint and unstable, barely visible even to the most powerful instruments. Their stars would be few, their structure incomplete, their light weak. But MOM-Z14 defies this expectation. It is compact, nearly 400 times smaller than the Milky Way, yet it radiates an intensity that suggests rapid and sustained star formation. In simple terms, it is producing stars at a rate far higher than models predict for such an early epoch. This creates a fundamental tension. Brightness in astronomy is not just appearance, it is a direct indicator of physical processes. A luminous galaxy requires large amounts of gas collapsing into stars, releasing energy in the form of radiation. This process demands both time and mass. Yet, MOM-Z14 appears to have both, far earlier than expected. The data, analysed through JWST's near-infrared spectrograph and supported by independent teams working under NASA and ESA collaborations, confirms that this is not a measurement error. The luminosity is real. The star formation is active. And that leads to a critical question. How did such a small system accumulate enough material to shine this brightly so quickly? One possibility is that star formation in the early universe was far more efficient than current models suggest. Gas may have collapsed faster, forming dense stellar regions in a fraction of the expected time. Another possibility is that the first stars were fundamentally different, more massive, burning hotter and faster, releasing enormous amounts of energy in short lifespans. But both explanations push against the limits of established theory. Because if galaxies could reach this level of brightness so early, then the pace of cosmic evolution is not gradual, it is accelerated, and brightness is only one part of the puzzle. When scientists examined the internal composition of this galaxy, what its light reveals about its elements, they encountered something even more difficult to explain. In 2023, as spectroscopic data from the James Webb Space Telescope was examined in greater detail, astronomers began to focus on something far more revealing than brightness: the composition of light itself. Using the near-infrared spectrograph, scientists broke the light of MOM-Z14 into precise wavelengths, searching for spectral lines, distinct markers that indicate the presence of specific elements. This method, refined over decades and used by institutions such as NASA and ESA, allows astronomers to determine not just how far an object is, but what it is made of. What they found was unexpected. Alongside the primordial hydrogen and helium, there were clear signatures of nitrogen. In simple terms, this should not be possible. Hydrogen and helium were formed in the Big Bang, but heavier elements, what astronomers call metals, are forged inside stars. They are only released into space when those stars die, often in violent explosions. For a galaxy to contain nitrogen, it must have already experienced multiple generations of star formation, and that requires time, Yet MOM-Z14 exists just 280 million years after the Big Bang. The timeline does not align. Stellar life cycles, even for massive stars, take millions of years. To build up detectable levels of nitrogen, stars must form, evolve, and disperse their material into the surrounding environment, then repeat the process. This suggests something extraordinary. Either star formation in the early universe was occurring at an unprecedented rate, or the first stars, known as population 3 stars, were far more massive and short-lived than current models predict. There is also another possibility. The environment within MOM-Z14 may have been extremely dense, allowing rapid recycling of stellar material and accelerating chemical enrichment beyond expected limits. But each explanation carries implications that extend beyond a single galaxy. Because if heavy elements can form this quickly, then the early universe was not just building stars, it was evolving chemically at a speed we have not accounted for. This is not a minor discrepancy. It challenges the sequence of cosmic evolution itself, and MOM-Z14 is not the only case. As more data emerges from JWST surveys, a pattern is beginning to take shape, one that suggests this galaxy may be part of a much larger population. To understand the scale of this problem, we must look beyond a single object and examine what else the universe has revealed. In 2023, as the James Webb Space Telescope continued its deep field observations, MOM-Z14 was no longer alone. What first appeared as a single anomaly began to multiply. Astronomers working through coordinated programs led by NASA, ESA, and international research teams started identifying more galaxies at extreme distances. These were not isolated detections. They formed a growing catalogue, objects with redshifts greater than 10, each representing a glimpse into the universe's earliest epochs. Among them was another confirmed system at a redshift of 14.32, existing just under 300 million years after the Big Bang. Individually, each discovery could be questioned. Measurement errors, lensing effects, or misinterpretations of spectral data are always considered. In observational astronomy, caution is essential. Extraordinary claims require verification, and verification requires consistency. But consistency is exactly what began to emerge. Across multiple observations, using the same instruments and independent analyses, a pattern formed. More than 100 candidate galaxies were identified at redshifts greater than 10. Many appeared brighter and more developed than theoretical models predicted. In simple terms, this was no longer a single outlier. It was a population. And populations change how science responds. When one object contradicts a model, it can be dismissed as an anomaly. When dozens, or hundreds, begin to show the same behavior, the model itself comes into question. The implications are significant. If these early galaxies are as common as the data suggests, then the process of galaxy formation in the early universe was not rare or delayed. It was widespread, rapid, efficient. This creates a widening gap between observation and prediction. The lambda-CDM model, which has successfully explained large-scale structure for decades, now faces tension at its earliest boundary. The issue is not that the model fails entirely, but that it may be incomplete when describing the first few 100 million years, and that leads to a critical realization. The universe is not just presenting isolated surprises. It is revealing a systematic behavior that we do not fully understand. To resolve this, scientists must now confront the limits of existing explanations and explore what mechanisms could account for such rapid formation on a cosmic scale. Because if this pattern holds, then something fundamental about the early universe is missing from our theories. By late 2023, the conversation had shifted. The question was no longer whether galaxies like MOM-Z14 existed. The data had confirmed that. The question now was how. Across research groups analysing JWST observations, a range of explanations began to take shape, each grounded in physics, each attempting to reconcile observation with theory, but none without consequences. One leading idea focuses on the first generation of stars, population 3 stars. These stars form from pristine hydrogen and helium, are thought to have been far more massive than stars today. If true, they would burn hotter, live shorter lives, and explode more violently, rapidly enriching their surroundings with heavier elements. In simple terms, they could accelerate the chemical evolution of the universe. But even this may not be enough. To produce the observed brightness and nitrogen levels in MOM-Z14 within 280 million years would require not just massive stars, but an environment where star formation occurs at extreme efficiency. Gas would need to collapse rapidly, with minimal delay, forming dense clusters capable of sustaining repeated stellar cycles. Another explanation turns to dark matter. In standard cosmology, dark matter forms the gravitational scaffolding for galaxies. If, in the early universe, dark matter halos collapsed faster or were more concentrated than predicted, they could have seeded galaxy formation much earlier. This would allow structures like MOM-Z14 to emerge ahead of schedule. More speculative ideas have also entered the discussion. Some researchers have proposed the existence of dark stars, hypothetical objects powered not by nuclear fusion, but by interactions involving dark matter. These objects could, in theory, produce significant luminosity without requiring traditional stellar evolution. However, the chemical signatures observed in MOM-Z14 strongly suggest conventional stellar processes are at work. This creates a tension. Each explanation addresses part of the problem, but none fully resolves it. Adjusting one parameter often creates inconsistencies elsewhere in the model. The stakes are now clear. If these galaxies cannot be explained within existing frameworks, then our understanding of the early universe, how matter collapsed, how stars formed, how elements were created, may require revision. And this is not a localized issue, because if the mechanisms behind MOM-Z14 are valid, they must apply across the early universe. To test this, scientists are now comparing these findings with other extreme cosmic objects, searching for patterns that extend beyond galaxies alone. By early 2024, the implications of JWST's discoveries began to extend beyond galaxies, like MOM-Z14. The telescope was not only detecting early galaxies, it was uncovering other extreme objects that appeared far earlier than expected. Among them were candidate supermassive black holes and luminous quasars, each observed at distances corresponding to less than 1 billion years after the Big Bang. These objects require enormous amounts of mass and time to form. Yet, like MOM-Z14, they appear ahead of schedule. This is where the pattern becomes difficult to ignore. Independent teams, analyzing data from JWST and supported by institutions such as NASA and ESA, began comparing these findings. The results pointed toward a consistent trend. Across different types of cosmic structures, galaxies, black holes, and quasars, the early universe appears more evolved than predicted. In simple terms, complexity is emerging too soon. The formation of a supermassive black hole, for example, requires either the rapid collapse of massive gas clouds or prolonged growth through accretion. Both processes are constrained by time, yet observations suggest that these limits may have been exceeded. Similarly, quasars, powered by actively feeding black holes, emit enormous amounts of energy. Their presence at early epochs indicates not just formation, but sustained activity. This reinforces the central issue raised by MOM-Z14. It is not only galaxies that are forming earlier. Multiple categories of cosmic structures are appearing in a compressed timeline. The stakes are now broader. If these observations are correct, then the early universe was not a slow transition from simplicity to complexity. It was a rapid phase of structure formation, where stars, galaxies, and black holes emerged in parallel, driven by mechanisms we do not fully understand. This challenges a foundational assumption in cosmology, that time is the limiting factor in early structure formation. Instead, the data suggests that the universe may have had access to processes that accelerated growth across multiple scales. The question is no longer confined to MOM-Z14. It is now about the nature of cosmic evolution itself, and as scientists attempt to reconcile these findings, a deeper implication begins to take shape, one that extends beyond galaxies, beyond models, and into the fundamental story of how the universe builds complexity. To understand what this means, we must now step back and examine the broader cosmic picture and what it tells us about our place within it. In 2024, as data from the James Webb Space Telescope continued to accumulate, one conclusion became increasingly difficult to avoid. The early universe was not evolving at the pace we expected. MOM-Z14, first identified through JWST observations and confirmed through spectroscopic analysis, remains one of the clearest examples. A galaxy existing just 280 million years after the Big Bang, bright, active, and chemically enriched, stands as direct evidence that cosmic structure formed earlier and faster than predicted. In simple terms, the universe did not wait. For decades, cosmology has operated under a structured timeline. Matter collapses slowly. Stars ignite gradually. Galaxies assemble over hundreds of millions of years. Complexity is built step by step, constrained by time and governed by known physical laws. But observations now suggest a different narrative. Across multiple independent studies conducted by NASA, ESA, and global research collaborations, early cosmic structures appear not as rare exceptions, but as consistent features. Galaxies, black holes, and luminous systems are forming in parallel, compressing what was once thought to be a long evolutionary process into a much shorter window. This does not invalidate existing models. The Lambda CDM framework continues to describe the large-scale structure of the universe with remarkable accuracy. But, at its earliest stages, something is missing. Some mechanism, whether related to star formation efficiency, dark matter behavior, or initial conditions, is accelerating the emergence of complexity. The stakes extend beyond astrophysics. If the universe can build structure this quickly, then the conditions necessary for further complexity, chemical diversity, planetary systems, and potentially even the ingredients for life, may also arise earlier than previously assumed. This expands the timeline of cosmic possibility, yet caution remains essential. These findings are recent. The data, while strong, continues to be refined. Future observations, deeper surveys, and more precise measurements will determine whether this accelerated formation is universal or limited to specific conditions. For now, MOM-Z14 stands as a marker, not just of distance, but of limitation. It defines the boundary between what we predicted and what we observe, and in doing so, it reminds us of a fundamental truth. The universe is not obligated to follow our expectations. It reveals itself on its own terms, often faster, often more complex, and often more surprising than our models allow. The story of cosmic origins is not complete, it is still unfolding.